All right, we are live and we have so many people. Welcome. Thanks everybody for joining. We have a really good session up today all about fresh data, keeping things fresh, pulling data out of a database, RAG, all the good stuff that you want to know about. And with us today, we have Stefan, who's a developer advocate at Zilliz and also a friend of the community running all of the Berlin meetups. So if you're in Berlin, look out for him. He's setting up sessions. And we have Saba and Andreas from the ML engineering team at Jina, who are going to show us some really cool things about clip embeddings. We have a lot to cover today, so we're actually just going to jump right into our first talk, which is Stefan, and we'll take some questions from the audience, and then we'll jump into the second talk and look at a couple demos. So it should be really great. Thanks, everybody, for taking the time and joining us. Stefan, whenever you're ready, your session should be up, and you can just jump right into things.
Perfect. Thank you very much. Yes, I'm going to start. And today I'm here to talk to you about how to keep your data fresh for mastering updates in vector databases in particular. You know, RAG is very popular and a lot of people are building demos around RAG, showcasing how you can do RAG. But no one really talks how to update your data, Everyone is always like, you insert it and then that's it. I'm going to try to show you how you can understand better how things work. We're going to go quite deep in the technical part for vector database. So yeah, let's get the focus. We're going to talk about how we insert the data, how we update it, the different tips I can give you so you can update your data. Let's get started. I'm going to start with myself. I'm Stefan Batifol. I'm a developer advocate at Zilliz. If you have any questions related to this talk, to GenAI, to Zilliz, Milvus, anything, RAG, the Berlin branch of the MLOps community, reach out to me with my email, LinkedIn, Twitter. I'm everywhere. I tend to reply very quickly. I'm going to talk about Milvus and what we are and what we're doing. So Milvus is an open source vector database. It's actually part of the Linux Foundation AI and data branch. And you might be familiar with it. We've been here since 2017, and a lot of people use it, like a lot of stars on GitHub. What's cool as well is that we built for scale. So usually our biggest customers have like billions and billions of vectors. We have different features, you can use like dense and sparse embeddings, filtering, re-ranking, different things. And what we have is also like we introduced it actually 2 weeks ago now. We have Milvus Lite, which allows you to use Milvus directly on your laptop. So let's say, in a notebook, also like Google Colab, but all you have to do is let Milvus look, and then you don't have to, worry about using Docker or deploying it on Kubernetes, which is what we were recommending, in the past. And yeah, everything will work locally. Everything can work everywhere. We have integration with like different AI toolkits. The usual, LangChain, Llama Index, Haystack as well. I'm not going to list them all. There's Jina AI as well, which we work with, especially for the embeddings and re-rankers. But yes, we work with like a lot of AI toolkits. That's all about the introduction for Milvus, what we are. I'm going to go more into the details. So I'm just going to talk quickly about RAG, and I guess if you're here, you probably used it already in the past, but I'm going to introduce it quickly, and then we'll go more into the technical parts. So RAG means Retrieval Augmented Generation. The basic idea is to use RAG to force the LLM to work with your data. So you inject it in a vector database, and then you can work with your private data. The basic RAG architecture is that one. So you have your data, you extract the content from your data. So it can be like, anything. It can be PDFs, it can be images, it can be like, different content, and then you chunk your data, and then you embed it and you store it in a vector database, like Milvus. Then you have your query from your user. You embed this query, you do a semantic search as well, then with Milvus, and then we're going to return, at least for the basic RAG architecture, we're going to return the top K, the top results for the similar data. We add this back to the context, we give it to your LLM, and then we give you a response. So that's like the basic RAG architecture. Everyone has been talking about it for like the past year. Everyone is working on it. It's quite cool. Now we have more advanced RAG architecture, but that's not the main goal of these talks. So yes, that's keep that in mind. It's going to be quite important. But then also, when I usually talk about like vector database in general, people are always like, why even use one? I'm not going to list everything, but there's like search, and then there's high performance search, and then there are like other things that are needed. It's like CRUD operations, so like create, read, updates, and delete can be a bit tricky if you don't use a vector database. Like you might have to rebuild the index yourself. You might have to delete the data yourself. It can be quite tricky, and you might spend all your time actually doing that instead of working on something else. Data freshness, which is what we mostly going to talk about today. So how to ensure that your data remains up to date, how to update your data, and different things, persistence, availability, scalability as well. You might struggle to scale if you're using, I don't know, like a plugin, or if you're using something that is like Face or something, for example. So usually we can help with that. Of course, like you introduce something new in your stack, but it can be really useful. Also, there's the data management part. So, like how do you do data ingestion, indexing, querying, those things can be a bit complex to do. And then there's backup and migration as well. So, how to back up your data, how to make sure you don't lose it. Those things can be important. Then there's the way to deploy. So like if you deploy on cloud or on premise, it can be a bit tricky as well. Observability, multi-tenancy as well. Those are like different points. So then I just list them. But yes. And then vector plugin. Some can be good. And it can honestly work for like, if you have a bit of data, but then if you actually go at one point to like scale, it can be quite hard, like maybe they don't offer filtering, like you might not be able to filter through non-vector attributes. Hybrid search might be also like difficult, like if you want to combine your vector search with your keyword search to have like a better search experience, maybe they don't offer that. Range search as well, which is a different thing. Scalability concerns, they usually can struggle to scale at one point. Or you might actually recreate a vector database in the end to make it scale. And also, like everything's changing so quickly that it may be hard to catch up and to follow. With that in mind, I'm going to introduce the design principles of Milvus. Basically, what we did and what we have is that the storage and compute is fully separated. We also use different, storage systems so that you never lose your data, and it also doesn't stay in memory all the time. So we use like mini IO or S3 to store your data. And then I'll go more into the details later, but you will also have like some data that is live, but then that is pushed then to the object storage. We also have microservices, so you can scale by functionality, meaning that we have on this graph, you see the query node, and then you see the data node, and then you see the index node. So those are independent to each other, and you can scale them up and down depending on your use case, depending on your needs. Let's say you have a lot of data to process, you have a lot of data to work with. Like, I don't know, you have a Spark job that is coming. Maybe you want to scale up your data node so that it can process everything, but you don't really need to scale up your query node because you're not really running any queries at the moment. So those are like the idea what we have. And it's really like everything is independent. So if you can, like if you have a lot of data coming, you won't struggle with it, and it won't have an impact on your index or on your query. So yes, that's the architecture. That's the same, but like with a bit more detail. And what I was saying before is that, you have the query node, which is cycled in red here. And this one is here to basically help you serving search requests. So it's subscribed to, let's say, if you use Kafka, then it's subscribed to it. So you have real-time updates for all the data that is coming. And then it's going to convert this data into what we call segments. And I will talk about those later, but they're basically in-memory structures that are temporary. And then it also has access to historical data that you store on S3 or mini IO or whatever you want. And this is also what allows you to perform hybrid search, to combine vector and scalar data. So then you have the data node, which you can see in orange. This one is processing the data updates. So this is what we're going to use, like to actually perform the updates. That's what we do. This one is performing the mutational request. It stores the different snapshots, that you may want to have. And yeah, this one is really here for the data updates. And then in purple, you have the index nodes, which is building the search indexes. So really, it's like this one is here to make like faster search operations. And what's very good with this one as well is that it can be implemented using a serverless framework. So you can really like scale it up and down. If you don't need to build a new index, you can fully like scale it down, and then you won't have to pay for it. That's what I was saying, before, which is like everything is independent. So that's like the good part. So yes, that's basically the architecture. For the entity, this is basically what's very important for Milvus and vector database in general. We all have our own entities, and you'll see like you have a primary key, a partition key, which allows you to split your data into different partitions. And then you have a fixed field, which is, which supports different data types. So like numeric, JSON, arrays, or different things. You have then dynamic fields, which allows you to store everything in JSON. So this one, you can like store everything that you want. It's dynamic, as the name is mentioned. And it's really like, if you want to like store some metadata or something and you don't really know the schema, then you can put it in dynamic field. You have then the vector field, and then you have like different things that are reserved for the system, which, helps you with like concurrency in general. I said we would go a bit into the details, but so this is one part of the Milvus data layout. So you have shards, and you can think of those like filling cabinets for data. So basically you divide your data into sections, and those are called shards, and they kind of act like a filling cabinets, and they're always managed by a supervisor, so by a leader. And this supervisor is really responsible for adding new information to the shards, storing the data in a safe place. So I was mentioning S3 before, that's what is doing it. Also is the one that is serving the latest information for the search request. And then it's forwarding historical data requests as well to the other cabinets if needed, so the other query nodes. We have then segments, which is the magic of Milvus usually, which is like you have two kinds of segments. So you have the growing segments, and you can think of those as like, inboxes for the new information. Those are in memory, and they're here for like super fast access and updates. So that makes sure that you always have access to the freshest data that is available, that you put in Milvus. If you have like something to update, it's going to go in your growing segment, and then we're going to update it, and then you have access directly to it. Once we have enough data, or once you do some different actions, then we move from a growing segment to a sealed segment. And this one is immutable. So this one will be stored on S3 or on disk, but it's not stored in memory. And then we build an index on top of it, and then you can search through it very quickly. But yes, so as a summary, you have growing segments for the latest updates, and sealed segments for like everything that is historical, where where we built an index on top of it. And yes, so then how the data gets added and accessed. So you have sharding, which is like, the large data sets are divided into smaller sections. And then we write everything into a log broker, so like Kafka. And you can think of it as like a list of to-do list for the data nodes. And then the data nodes, they add the new data to the shards. They remove the outdated data if needed. They flush the accumulated data in a permanent storage. And then we create segments, so, growing segments, and then we shield them. And then we build index on top of it. And that's how it works, basically. That's what everything happens when you add data to your vector search and vector database in general. So that's also the thing of like, when you build a POC, you may be able to use face, for example, or different, libraries. But then it's actually a lot of work to actually make sure that, everything works and everything can scale. And that's why you might want to use a vector database. Then you have the data query, which is, as I said before, it helps you like search through your data and give you like results. So this one, it's really going to search through like different collections for like a k number of vectors that are near a target vector, or then all the vectors as well within a specific range as well, depending on your query, depending on your data query. So yeah, basically that's how it works. but then how do we handle data updates, and I'm going to talk in Milvus in particular here, but then the idea is the same. So a couple of things to avoid, I would say. First, if you want to be able to update your data and your documents, is to avoid, having like auto increments for primary keys or different things like that, because then you won't be able to, find them again. Or like if you go through the same document, then, if you're auto incrementing, you might be lost at one point. Also avoid generating IDs based on something you don't know. What I mean by that, is that sometimes, if you use different tools like LlamaIndex, LangChain or something, they will actually generate an ID for you. But just be careful on like how they generate this ID. Sometimes they can be very useful. I'm not saying it's bad, but they can generate ID based on the document. But then you have to make sure that you know what the document is. What is the definition of a document for LlamaIndex or LangChain? So like those things are are very important, because then you need them to be able to update your data. So then you have different strategies. You have unique identifiers. So, as I was saying before, so you can use like documents or an image or a vector, but you have to make sure that each piece has a unique identifier. So maybe you want to assign a UUID, to your documents or to your vectors, so that you can then, identify them, retrieve them when you want to make an update. Maybe you want to do metadata tagging as well, You want to do you want to attach some metadata to each data, and then you can do some quick search. So example, that created author or content type, and then you can filter on those. You can be like, okay, I want to filter on everything that has been written by John Doe, or every content, like every research paper, or everything that has been created on a specific date. Then you can search for those, and then it can be really helpful if you want to update everything, every document that has been written on the 6th of June, for example. You can also have composite identifiers. So, how to have like multiple fields to create then a unique one. Don't know when you would need that, but like you can be like, this user for this specific date with a specific timestamp. And then you can be like, okay, I want to update everything that has happened for this specific timestamp for this user, because, I don't know, there was something wrong, or you have new data about this user. So you can also do those. Then you have hierarchical IDs as well. So if you have some complex data sets in general, like you can use ID like project A, chapter 1, section 2. And then, if let's say you're going to use a new embedding model, and then you want to update your data, for this specific section, then you could update only this specific section. So those are usually like useful ways, I would say, to like update your data. And that's like allows you to basically still be the one in charge for your data. If you don't have that, then for example, for this section, depending on your chunking strategies, or depending on your, how you divide everything, you might not be able to refine this one actually, because LangChain might give you an ID for this section, for this chunk maybe. But then if you have a different chunk strategy, then you will never be able to find it again, basically. And yeah, so then let's say you have like those different strategies. If you want to do an update, with my Milvus, we have an upsert. So you can have like this data, with, ID 0 with a vector, and then with different information. ID 1 with a different vector, ID 2 with a different vector, and then you're going to say, please upset for this specific collection, and with that data. So then Milvus, as we saw before, they will check for your data. They will check if you have this ID already in Milvus. If you don't, then we're just going to insert it. And if you do, then we can update it thanks to this ID that you provide. You can also, as an example, you can also do it like for a partition. If you like decide to divide your data per partition, then you can do the same as we did before, except that you're going to add the partition name. So that really helps you, like to filter the data that you don't want, and to only take the one that you want. You can also, like as an example, this is how to upsert entities with LangChain. So, you have your documents, and those ones you have like specific documents, and then you add the metadata, and then you're going to add all those documents to Milvus, and then you can say, please, for all the IG in 1, 2, we're gonna do like here we're deleting, and then we do an upsert. So that's like, it's also a way to do it with LangChain. That's just an example just to showcase basically what we can do. And yeah, basically what happens then behind the scene is that you need to identify the data that needs an update. So, like make sure you have the primary key, within transfer the data to the proxy. We send, like the upset request to Milvus, and then we go to the proxy service. Then we talk with the data coordinator, which checks if you have a primary key. Then we do an upsert. And so, as I said before, either you update or you add the new document to the collection. And then, it's not over yet. You have the data allocation indexing. So you add your data in the growing segment. Then we assign the segment, to them, like a data node is assigned to the segment. Then we create, a segment number so that we can store it. Then we flush the segment at one point when it becomes too big. And then you have your SIL segments. And then we write it to S3, we put an index on top of it. And that's then how you can have, access to your updated data. And that's how you can update your data in general when you have a rack system, and make sure that, you have the latest data available. That's what goes behind the scene. I think I am out of time, so I'm just going to say thank you. Check out Milvus.io website. Check us out on GitHub as well, sorry. And if you have any questions, you can connect with me. Thank you very much.
Thanks, Evan. Awesome talk. Thanks so much for doing that. That was really interesting. I didn't know that Milvus had a totally local version that you could run. Would you ever think about using that for production, or would it very much just be like for development testing things?
Yeah, it's really for development testing. It's like, it also has a limited offering. So it's really cool, like you work on your own laptop, and you try to do your POC for your own rack system or something, and that's usually how you use it.
Yeah, it would also be nice potentially for some testing, like for CI testing.
That can also be, that's actually a good idea.
Yeah, super cool.
Everything.
Love that. Cool, awesome. Thanks so much. Yeah, I think good timing on that. We'll jump in to let Saba and Andreas give their talk next. Stefan, I'll take you off. And we'll see you in a bit. Thanks.
Thank you.
Okay. Hi, everyone. I'm Saba, and I'm here with Andreas. We are machine learning engineers at Jina AI, and we work on developing state-of-the-art embedding models. For example, last year, we produced the first open source embedding model that supported 8K sequence lengths. And after that, we produced a couple of more bilingual models as well as re-rankers. You can see all of them on our Hugging Face, and we also support API if you want to use it. And today we are very excited to present our latest model, which is a multimodal embedding model, Jina Clip. So basically, I will start talking about what Clip is. I'll give you a general introduction into what we did with our Jina Clip, and then Andreas will go into more details and explain training procedure more thoroughly. And lastly, I'll show you a very simple demonstration on how to use Jina Clip with vector search. So what is Clip? Today, what we call Clip is a family of models that are contrastively trained on language and image. So basically, Clip models learn a joint representation for text and images, and this enables us to solve tasks like multimodal retrieval, also zero-shot image classification, and many other tasks. This is especially relevant today for, I would say, multimodal retrieval that is widely used in RAG applications. So you basically have text or image as a query. You encode it into a shared representation. You have also a set of images or texts that are also encoded, and then you search through your text, images, or both together to find the most relevant one. So I mentioned contrastive training, and maybe I'll give you a very short introduction on what this means. So Clip is trained contrastively, and as you can see, we have Clip contains like two submodels, like two encoders, one for text and another for image. And what we do is that during training, we gather a lot of text-image pairs. This can be text images with their captions, for example. And then we encode both modalities with their corresponding encoder. And after this, our aim is to maximize similarity between embeddings of image and its corresponding text, which we call positive examples, and minimize similarity between image and any other random text that we have in our batch, which we call negative examples. So that's where the word contrastive comes from. Basically, Clip learns relationship between text and images by contrasting these positive and negative examples. And the bigger the batch, the more positive examples we have as well, the more negative examples we have. So it's usually better to have a big batch. Okay, so that's how Clip is trained. And now maybe a question like, why did we decide to train our own Clip model? So basically, we noticed that there are some deficiencies in the text tower, the text encoder part of the Clip model. Mostly, these deficiencies are that the previous Clip models, in most of the cases, the text tower weights are randomly initialized. And during this contrastive learning that I described in the last slide, this text tower does not have enough text during training to learn and understand the language properly. So eventually, we got a text encoder that does not have good language understanding capabilities. Also, the text tower is optimized contrastively to images only and not to other texts, right? Another issue is that most of the image text datasets that exist contain captions of the images, but these captions are usually very short. And you can imagine when you train the text encoder and only pass the very short captions, then this encoder cannot generalize to longer text, and also it's difficult to represent the language and understand the language with only short text captions. And also, previous works to save computational costs, they clipped the context length, and they used a very small context length. So, for example, the smaller models use 77, and the bigger ones use 32, which is not enough for a good text performance. And as a result, most of the Clip models do not have strong text encoders. And in production, this is a bit inefficient because when we have models, we not only have cross-model retrieval, for example, but we also want to use our models with respect to text-only tasks. And since the Clip model and the text encoder of the Clip model does not work well with the text-only tasks, in production, developers have to store two separate vectors for their texts. One will be one which is used with respect to images and is encoded by the Clip text encoder, and another that is used with respect to other text and text-only tasks. And for this one, they usually use the text-only embedding models. So we basically tried to improve these deficiencies, and the main idea, and Andreas will talk about this more thoroughly, but what we changed is that now, instead of only contrastively training on text and images, we add another objective, and we jointly optimize our model on text-image pairs as well as text-only tasks, right? So as you can see on the illustration, during training, we train our model on text pairs only and use the inference C loss for that. we also do what I already described in the last slides, this text-image contrastive learning, and then we jointly optimize on these two objectives. So our training is multi-stage. We have 3 stages. So I'll shortly cover right now, and Andreas will talk about each of them in more details. So basically, we start with, as I said, we have 2 objectives. In the first stage, we use mostly image text pairs with short captions, because that's the most of the data we have, and that is publicly available. On the second stage, we improve text image cross-model understanding by adding long caption, adding text image pairs with long text. And on the third stage, we use, instead of pair tuning, we use triplet tuning to further improve the text-only performance of our model. So this is the basic overview, and now I'll let Andreas to continue and talk about the training in more details.
Okay, great. I am Andreas. Hi. As Saba started telling you, we have like a multi-stage training. At the first stage, we did the usual clip training that Saba explained before. And we initialize our 2-word encoders through Jina BERT model that is also the backbone for Jina Embeddings v2 that supports 8K context length. And the image encoder was initialized with EVA2 vision transformer. These 2 entities have different losses. So we train jointly on multimodal tasks, that is caption and image. And also we train on a text pair. From the text, we get an inph loss, whereas from the image text pairs, we get a clip loss. I will tell you the difference in a moment. And combining these 2 losses, we get the final loss for our first step, for our first stage. Basically, the pairwise training for the text-to-text data. We choose the data mainly through scraping the web and some datasets. We use semantically related pairs like titles and paragraphs, or question answering datasets, and then we do a pre-processing to mainly filter out the pairs that couldn't help us. This has rule-based filtering that we mainly remove from the data URLs and things like that. The duplication to remove duplicates from the dataset, and also consistency filtering that removes the bad pairs from our datasets that we selected them but with not really good quality. So this text pair is input to the text encoder. As you can see, we basically get a pair, have the embeddings, produce the embeddings through the model, and then compute the cosine similarity. This creates a table similar to what Saba showed you at the first slide, where we choose the diagonal for the positive pairs and the non-diagonal for the negative samples. So for the clip loss, for the clip part, we used the Lion 400 million dataset. That's a dataset of 400 million pairs, image text pairs from a common crawl between from 2014 to 2021. And this dataset, the original common crawl is like 13 billion pairs. And to keep the 4 million pairs, we just use the original OpenAI clip to filter like the most similar pairs to have the better quality from this huge dataset. So how the clip loss in a similar way. Here we have on the left side, we give us input to the text encoder a caption, and to the image encoder an image through our models, and we compute the cosine similarity as the first way. So the difference between infancy and clip loss that we say is that clip loss has just a learnable parameter that changes during the training. But other than that, the losses are the same. For the first side, for the first stage of training, that is the biggest one, as was basically the main contrastive learning training, as on all clip models is done. We trained with a context length of 77 for computation costs in order to fit a big batch size of 32K for a total steps of 60K. This means for around, we saw during training 2 billion pairs, around 2 billion pairs of image text and 2 billion pairs of text-to-text pairs. After this stage, we just took the checkpoints, and what we changed here is like we wanted to give our model the capability to understand longer texts. To do that, we found a long caption dataset, which was like 1.2 million image text pairs, and the captions are from 100 to 750 tokens. As you can see, this dataset created with shared captioner. Basically, they took image text pairs that there were already on the common pool. They add their model, shared captioner, and this is the generated captions. So here we also have the link if you want to check the model. And so we use this model to get the long captions. So for this second stage tuning, we trained much, we didn't train so long as the first one, as we didn't have also so much data. The text pair here are the same, and the image text pairs are the long captions. Totally context length 512 for 7,000 steps. And for the third stage, that we basically wanted to have all the previous methods were like unsupervised methods, but now for our text encoder to get better text-to-text capabilities, we needed to do a supervised training. And that's why you use the pairs plus hard negatives. For the image and text, for the multimodal pairs, they remain the same thing, the dataset. So here, what are the triplets? Basically, we mine triplets in order to. Right now, we don't create our negatives. It's like the previous stages that we have positive pairs and negative pairs, but we don't create our negative pairs randomly from the dataset. We have already decided what is the negative example, and so this on this stage we could do a contrastive training by comparing answer, which is a query, with our positive example against the answer and all the negatives examples. So in that way, we wanna get our query positive example together in the space, whereas move away from there the negative examples. This was also not a really long training stage. We trained again with a context length of 512 for 12,000 steps. Our models basically has trained until a context length of 512, but because of Alibi that is used on Jina implementation, this can extrapolate till 8K context length, and it can be supported in a pretty nice way. This was basically our model. What we wanted to achieve with this model was mainly to have one common model for multimodal retrieval and text-to-text retrieval in order to save all the embeddings in one space. And here you can see the performance differences. As we told you before, in the text-to-text, the original clip models doesn't perform well, whereas here Jina Clip V1 has a performance close to Jina Embeddings V2 on the MTB retrieval datasets. And we also achieved to have slightly better performance on all the multimodal tasks, on all multimodal retrieval tasks than the original clip version. So at the end, what we wanted to achieve and we managed to achieve with this paper was like to encode both images and text in one paper, in one model. One model basically to do all the jobs we needed before in a RAG pipeline. We managed also to achieve a strong performance of text retrieval, and we are pretty pleased with that. If you want, you can find our model here on Hugging Face or through API. And now Saba will give you also a presentation for a small demo we created.
So basically, this is a very short and simple demonstration on how you can use Jina clip. Initially, I wanted to have a multimodal RAG example with Llama Index, but it looks like Llama Index does not yet support open source multimodal embeddings from Hugging Face. So I had to choose a bit more like a simplistic demonstration. And in this case, what we're going to do is we'll use Jina clip with our open source library Dockeray. And Dockeray supports in-memory, very simple vector store. And we're going to use this vector store to do the some vector search on our multimodal documents. Basically, I start with installing the required libraries. Then we need to load the Jina clip model, which you can do like that. This one important thing is that you have to pass the trust remote code equals to true, because this Jina clip v1 relies on our custom implementation, which you also can see on the Hugging Face. So it's open, but we have to pass this. So the model is loaded. Now regarding data, this is, as I said, is very simple example. So I have a list of some texts regarding different animals, and I have image URLs also regarding some animals. What I'll do is that I'll create in-memory exact nearest neighborhood index using Dockeray. Basically, what this is that this is an in-memory index which loads all the vectors you have in memory when you use it. This is good for the cases where you don't have a lot of documents, because it doesn't need like some extra dependencies, and also it doesn't use any approximate search algorithms. It just iterates over all possible vectors you have in the index and finds the most relevant one. So in case of if you have small amount of documents, this is a pretty good choice for RAG, and not just for RAG, but also for vector search. What we do is that we define a document schema. In our case, our document will contain like a modality. So it might be text or image. It will contain an embedding. So these two fields will be required, and also depending on which kind of document it is, it might contain the text, so the original sequence, or the URI, which will be the URL of the image. So I define the schema and I pass it to the in-memory document index to create a document index using Dockeray. So the next part is to actually create those documents and index them. What I do first is that I create the text documents. So for each sequence in the list of the sequences I have, I first of all embed that sequence by calling the model.encode text. So after you load the model from Hugging Face, you can use encode text to encode your text documents. And I fill the other keys as well. After my text documents are ready, I'm just indexing them in my document index, and I'll do the same for image documents. The only change is that instead of encodes text, what I'm calling encode image, and then we can index the documents we have. It's been indexed, and now what can we do? We can search using our queries. Let's let this be our query, this Buddha frog statue. we first need to encode this using our clip model, and then we can call the find function, passing the query, passing the field that we're doing the search on. So this should be the embedding field. And also for this case, I'm just going to retrieve one document. And let's see what it returned. So it returned this text sequence that was regarding the frog as well that we had here. And now if we want to search through only images, for example, what we can do is build a bit more sophisticated query, which also consists of filtering. So basically first we filter on the modality, we only keep the images, and then we do the same, find only on the images that we have left. Limit is also 1, so this will return one document only, and hopefully this will return the image of the frog, which it does. And yeah, basically this is a very short example of how to, well, first of all, load our model from Hugging Face and utilize it with a very simplistic case of vector store, but you can do this for other vector stores as well. Or, I mean, once Llama Index supports this kind of models on Llama Index as well. But if you still want to use it with Llama Index, what you can do is, so it already supports Jina API. You can go to jina.ai/embeddings, generate API key. You will have 1 million free tokens initially, and you can use it very easily. So I think that's it from the demo side. And now maybe if there are any questions, or we can also discuss that.
Thanks so much for showing that. That was awesome. I really liked seeing it. I have to imagine you could have also done that using Milvus and the new on-system vector database to store those Jina embeddings, right?
Yeah, of course.
Super cool. That's awesome to see. How did you guys start working together, Jina and Zilliz?
I invited Bo, which is head of engineering, I think, at Jina AI, to an event because I'm based in Germany and I work with like German English documents, and Jina AI has like an embedding model which is multilingual, so you can use it with like German and English. And I started using it and I've seen like how much better it was than the other embedding models. So then I reached out. I was like, hey, do you want to talk about it at a meetup? And then they did. And then I was like, oh, actually, it could be cool to have direct integration of Jina into Milvus. And so now we have it as well for like, the different embedding models and rankers as well that Jina is offering.
That's super cool. Is the model that you guys were just showcasing in Jina a multilingual model as well, or is it focused on English?
So right now, this clip model is only English, but we want to also develop a multilingual clip.
That's super cool. Yeah, I don't think I've seen I'm sure there is one, but I haven't seen a multilingual, multimodal model.
Yeah, it would be cool.
Yeah.
There are some, but the problem is like there is not really easily supported in the Hugging Face. There are some different problems, and the problem we also said.
Yeah. Are you guys working like sufficiently down at, for example, like the tokenizer level for non-English languages? Or is it something you take from the open source community when you're working on these models?
We had our own BERT implementation as well, including this tokenizer and everything. We also experimented with the existing backbone models such as XL and Roberta. And yeah, it's in progress right now for the multilingual ones. So the bilingual ones that Stephen mentioned, it was our own. So like starting from zero in tokenizer and everything was based on our own implementation.
That's really cool. That's awesome. What's coming up on the agenda, I guess, for both, for Milvus and for Jina?
Then so I guess we're trying to become more multilingual in both fronts, like just text-only models as well as multimodal embedding models, and that is probably the main direction we have right now.
Yeah, and for us, it's like even more, things with like Milvus Lite in general, and like different integration with like partners, I think.
Very cool. And when the last time I was using Clip, it was a little while ago, but I was using an Onyx compiled version of Clip embedding model. Are you guys working in that direction as well for like the lower compute available teams?
I think there are Onyx integrations. Hugging face models for sure.
Nice.
We have Onyx integrations.
Great. I mean, we're pretty much at time. I really appreciate all of you guys joining and everybody who's listening, and thanks for Zilliz for sponsoring this session. It wouldn't be possible, and all the future ones that we do. So thank you very much, and have a good one. Thanks, guys.
Thank you for hosting. Thank you, everyone.
Bye bye.